Explore advanced list operations in Python, including comprehensions and nested structures. Understand sorting algorithms and memory management techniques to optimize performance. Mastering these concepts enhances code efficiency and readability, crucial for developing robust Python applications. List comprehensions offer a concise syntax to transform iterables into new lists using elegant one-line expressions. They provide a performance boost by executing faster than traditional loops due to optimized internal mechanisms. This approach enhances readability, allowing developers to write cleaner, more Pythonic code that's easier to maintain. List comprehensions offer a concise way to create lists by applying expressions to each item in an iterable. This approach is more readable and efficient than traditional loops. For example, instead of using a loop to append squares, use x squared for x in range 1 to 5, resulting in 1, 4, 9, 16, 25. List comprehensions follow a simple pattern. Expression for item in iterable if condition. The expression defines the operation. The iterator variable represents each element, and the iterable is the data source. An optional condition filters items. For example, x squared for x in range 1 to 5 generates squares of numbers 1 to 5. List comprehensions dramatically reduce code lines, transforming multi-line loops into concise expressions, enhancing maintainability. They improve readability, making code self-documenting and easier for developers to understand. Python optimizes comprehensions for superior performance over traditional loops. Advanced features like filtering and nested loops make them versatile for complex data transformations. Advanced list comprehensions allow for generating combinations using nested loops, such as pairs equals open parenthesis x comma y close parenthesis for x in range, open parenthesis 3 close parenthesis for y in range, open parenthesis 2 close parenthesis, resulting in open parenthesis, 0 comma, 0 close parenthesis, open parenthesis, 0 comma, 1 close parenthesis, open parenthesis, 1 comma, 0 close parenthesis, open parenthesis, 1 comma, 1 close parenthesis, open parenthesis, 2 comma, 0 close parenthesis, open parenthesis, 2 comma, 1 close parenthesis, close parenthesis. Conditional expressions enable operations based on conditions, like transformed equals, open bracket x, if x%, 2 equals 0, else minus x, for x in range 5. Close bracket, yielding open bracket, 0 comma, minus 1 comma, 2 comma, minus 3 comma, 4 close bracket. Nested lists in Python allow for the representation of complex data structures like matrices, tables, and grids. They enable flexible access through multiple index operations, making them ideal for real-world applications such as game boards, spreadsheets, image pixels, and scientific data analysis. Nested lists are hierarchical structures where lists contain other lists, enabling complex data representation. They're used in mathematical matrices, spreadsheets, game boards, and image data. For example, a 3x3 matrix can be represented as a nested list, allowing for intuitive data manipulation and access. Accessing and modifying nested lists involves using double indexing. For instance, matrix 1, 2 retrieves the value 6 from the second row, third column. To modify, assign a new value, matrix 1. 1 equals 99 changes the center element. This indexing mimics a coordinate system, allowing precise data manipulation within the matrix. Iterating over nested lists involves using nested loops to access each element systematically. The outer loop traverses rows, while the inner loop accesses elements within each row. This approach prints elements horizontally, row by row. Alternatively, index-based iteration allows precise access, printing each element's position and value, enhancing understanding of matrix structures. Nested lists elegantly represent game states in tic-tac-toe. The board is initialized with empty spaces. Player X moves to the center, player O to the top left, and player X to the bottom right. The display board function visually represents the board, showing how nested lists map to grid-based mechanics, with indices corresponding to board positions. Python offers robust sorting capabilities with built-in methods like sorted and .sort. These functions allow for performance-optimized sorting, with options to customize behavior using key functions and reverse parameters. They can handle complex data structures, including tuples, dictionaries, and custom objects, making them versatile tools for data manipulation. Python offers two primary ways to sort: the sorted function and the .sort method. The sorted function returns a new sorted list, leaving the original unchanged, and works with any iterable. In contrast, sort modifies the list in place, returning none, and is exclusive to lists, offering slight memory efficiency. Python's sorting functions default to ascending order, arranging numbers numerically and strings lexicographically. For instance, integers like 42, 7, 23, 15, 8 become 7, 8, 15, 23, 42. Strings such as zebra, apple, monkey, banana sort to apple, banana, monkey, zebra. Note: uppercase precedes lowercase. Use key equals str.lower for case-insensitive sorting. The key parameter in sorting allows for custom sorting logic by transforming elements before comparison. For instance, sorting words by length: is, and, Python, awesome, powerful. Numbers can be sorted by absolute value: 1, 2, -2, 3, -5, -8. Custom functions, like sorting by last character and lambda functions for inline keys, offer versatile sorting options. Reverse sorting in Python is straightforward with the reverse parameter. Use sorted or .sort to arrange elements in descending order. For example, numbers equals 3, 1, 4 becomes 4, 3, 1 with reverse equals true. This parameter also integrates with custom key functions, enabling complex sorting criteria in reverse order, like sorting words by length. Python excels at sorting complex structures like lists of tuples and dictionaries. For instance, sorting students by grades in descending order is achieved using a lambda function. Similarly, dictionaries can be sorted by scores using a key function. Multi-level sorting is possible by combining criteria, such as sorting by grade and then by name using item getter. Visualizing sorting helps understand its impact. Consider an unsorted list: 42, 15, 73, 28, 56. Sorting it in ascending order results in 15, 28, 42, 56, 73. This transformation highlights how sorting organizes data, making it more accessible and meaningful. Such visual comparisons are crucial for grasping the efficiency and utility of sorting algorithms. Understanding list copying is essential. Assignment creates a reference, not a copy. Shallow copy duplicates the structure but shares nested objects, leading to potential side effects. Deep copy, however, recursively copies all nested objects, ensuring complete independence. This distinction is crucial for managing data integrity and avoiding unintended mutations in complex data structures. Understanding why we copy lists is essential to prevent unintended mutations. Assigning a list to another variable creates a reference, not a copy, leading to shared changes. To work with independent copies, we must create true duplicates, ensuring changes to one list don't affect another. This knowledge aids in testing, backups, and parallel processing. A shallow copy creates a new list object, but shares references to nested objects. Methods include .copy, list, and slice notation. For nested lists, changes to shared references affect both original and copy. Shallow copies suit simple lists, but not nested structures, as they only duplicate the top-level structure, leaving nested elements linked. A deep copy creates a fully independent duplicate by recursively copying all nested objects. Using copy.deepcopy, changes to the copy don't affect the original. This is crucial for nested lists, dictionaries, or custom objects when absolute independence is needed, such as in undo/redo functionality, test fixtures, or parallel processing with isolated data. In a shallow copy, a new container is created, but nested objects remain shared references. This means changes to nested objects affect both the original and the copy. In contrast, a deep copy creates fully independent structures, ensuring no shared references, providing true independence between the original and the copy. List comprehensions offer a concise syntax for transforming iterables, ideal for data transformations. Keep expressions simple. For large datasets, consider generator expressions. Nested lists are perfect for multidimensional data like matrices. Use double indexing and consider NumPy for intensive tasks. For sorting, use sorted to preserve lists, .sort for in-place efficiency. Deep copy nested objects to avoid bugs. Explore Python's list documentation at docs.python.org for deeper insights. Access complete code examples and practice exercises from the course repository. Challenge yourself with sorting algorithms, matrix operations, and data transformations. These foundational concepts are crucial for tackling real-world programming challenges. Happy coding!